Hello. In quantitative analysis, quantitative kinematic analysis, we are trying to understand the motion and quantifying the motion. So, wherein we are trying to do the velocity analysis and the acceleration analysis. Now, for velocity analysis, one method is to use the relative velocity method, where we are using velocity polygon to determine the velocities of the points in the given mechanism for the given configuration. And another method is of instantaneous center method. Now for that we need to understand what exactly is an instantaneous center of rotation. Now before we understand what is instantaneous center of rotation, we will just try to recapitulate what we exactly we have been the considerations in plane motion of a rigid body. So all the bodies, we are considering them as the rigid bodies or resistant bodies. So now for a plane motion, that means the motion is planar, that we have considered, right? So whatever mechanisms under consideration right now, they are all planar. So in plane motion, if we see when a body is in a plane motion, the angular motion of the rigid body is same as that of a line on this body, and this line is on the rigid body and it is on the same plane. This is one understanding for a plane motion which we have seen. The second understanding is that the angular velocity and the angular acceleration for a body which is rotating, having a planar motion, they are perpendicular to the plane of motion. Fine. And the third consideration, so this is for, if we see, like when we are considering a mechanism, for example, it is, let us say, a slider crank mechanism, wherein we can see that the crank is having a pure angular motion, the slider is having pure linear motion, which is translation. So this is rotation, this is translation. But if you see this body, the connecting rod, which is called as well as the floating link, it is having combination. So I can say that this is general motion. So this general motion of a body, this will be definitely composed of rotation and translation. Right? This is what we have understood as motion of a plane motion of a rigid body, or when the rigid body is moving or having motion on a single plane. Now comes the question then, what is exactly an instantaneous center? Now, so we can define what is an instantaneous center of rotation. It is that for a rigid body in a plane motion, there exists a point on maybe the rigid body. Now this point may be on the rigid body, or it may lie beyond the physical boundaries of the rigid body, whose instantaneous velocity is 0. So how we can define it? So for a rigid body in plane motion, there exists a point. Now whatever this point we are talking about, this point may be on the body itself, or it may be beyond the physical limitations of the body, whose instantaneous velocity is 0. So this point is called as the instantaneous center of rotation, or the IC. So if there is kind of, say, let us say this is a rigid body which is having a planar motion, it is under plane motion. So there exists one point, right? Now that point may be on this body somewhere here, or maybe this point may lie beyond the physical boundary of this body, and whose, that means this point under consideration, its instantaneous velocity is 0. Now if the instantaneous center of this point is 0, then we can assume or consider that as if this body is rotating about this point. So in that case, for this instant, I can call this point to be as the center of rotation for this body. Now again, let me tell you, this is an instantaneous center. So for the next instant, maybe the instantaneous center location for that body may change. Now for this instant, this body is rotating about this particular point, whose instantaneous velocity is 0. Now this is what is an instantaneous center. So in that case, now there will be a need to prove that there is existence of such a point in a body. So to prove the existence of instantaneous center of velocity for a rigid body. So we need to express it or understand it or prove it mathematically that such a point do exists, that for an instant the instantaneous velocity is 0. Now for that, let us consider a body. Now as we have understood, for a motion, a rigid body in motion, the motion of the body will be same as that of a line on that body. So let us say we consider one line on this body. We name it as, say, A and B. Now this AB will have the same motion on this plane as same as that of this rigid body. So maybe let us say this is having motion with angular velocity omega. Now if this is the condition for this instant, then we can say that the instantaneous velocity of point A and point B can be expressed. Now if that is the, if it is turning this way, let us say the instantaneous velocity vector for A is something like this. So let us say this is velocity of A. Now if I know the condition of what is VA and the motion omega, in that case definitely I will be able to predict what is the instantaneous velocity of B. So if it is turning this way, so maybe B is moving, say let us say the instantaneous velocity vector for B is this. Now my line of reference is AB. So with respect to AB, if we see, say this angle with respect to AB, this is some angle phi, and with respect to AB, say this angle is theta, right? So now if I draw or if I go for a construction and I consider two lines, right? One is perpendicular to the velocity vector, for B, and one line perpendicular to the velocity vector of A. Now these two lines are going to intersect somewhere here. So here I name this point as I. Now here I have got this point inside the body. This point may as well come outside the physical limit boundary of the body as well. So anyway, wherever I get this intersection where these two IA and IB, they are perpendicular to the vector VA and VB. So if we see the geometry, in that case this will come out to be 90 minus 5 and this will come out to be 90 minus theta, right? Now so if I consider, so let us talk about these two velocity vectors. Fine. Now if we see the components of these two velocity vectors along the line AB. Now when this is in this direction, so this is one component of velocity vector VB, and along the line AB this will be the other component of, so this is velocity of A cos theta, which is a component of VA along AB, and this is VB cos phi, and so this component is the velocity component which is along the line AB. Now this body is a rigid body, that means distance between A and B is not changing. So if this body, so whatever, so these two components which are along the line AB, they are causing to move this body maybe in the direction of AB or along the line AB. So along the line AB, if we see, when this is a rigid body, the distance between A and B is not going to change. So that means I can say the velocity, these two components, A cos theta and VA cos theta and VB cos phi, which are along the line AB, they will be same, because when distance between AB is not changing, maybe after some time delta t, it is moved by this, so displacement of B and A will be same at the same given time. That means these components along the line, they are same. So I can say that velocity of A cos theta will be equal to velocity of B cos phi. So in that case, then I can say that velocity of A upon cos phi will be equal to velocity of B upon cos theta. So I can name this as, say, the equation 1. Now I consider So triangle, now I consider triangle IAB. So here we consider the triangle IAB. Now when we apply the sine law to this triangle, so what do we get? Sine law we are applying, so this, for this opposite side is this, so I can say IA upon sine of 90 minus 5 will be equal to, for this opposite side is this, so IB upon sine of 90 minus theta, and sine of 90 minus 5 will be cos phi, so I can say IA upon cos phi will be equal to IB upon cos of theta. So say this is the equation number 2. So when we compare these two equations, I can very well say that velocity of A upon cos phi, or velocity of A upon IA will be equal to velocity of instantaneous velocity of B upon IB, and this will be definitely, in that case, will be equal to omega. See, so I can say that VA is IA omega and VB is IB omega. So linear velocity, if we see instantaneous velocity, is R omega. So that means IA is acting as R, radius of rotation, and omega, it is the same body. So omega for the body, if it is the same body, the omega is same. That means I can say that IA and IB, they are acting as the radii of rotation correspondingly for A and B. So I can say in that case, this A and B both, they are rotating at this instant, they are rotating about I. So this becomes the center for rotation, and that means I can say that the velocity, therefore I can say the velocity of the point I is 0. So if this is so, then in that case I can say that the point I is the instantaneous center for rotation for body, this rigid body under consideration. So now in a mechanism, so we have just now seen the instantaneous center by understanding motion of only a single body. Now if we consider a mechanism, in a mechanism there will be number of links involved. So say this is link number 1, this is link number 2, this is link number 3, and say this is link number 4. So maybe I fix this one as the frame. So this is so in a mechanism, then these bodies, they are interconnected to each other, and so now when there are number of bodies which are having relative motion with respect to each other, then there will be existence of relative instantaneous centers. By, let us try to understand, when there are two moving bodies, so two moving bodies, they are moving relative to each other. Let us say the link 2 and link 3, they are in relative motion. Then we can define a relative instantaneous center. They are in relative relative instantaneous center as, let us say, we name it as I as the instantaneous center. So instantaneous center I23 as a point on, say, link 3 or body 3, on the link 3 or body 3 having zero instantaneous velocity, having zero instantaneous relative velocity with respect to a coincident point on the link 2 or the body 2. So that is how we can say. So we can define a relative instantaneous center as I23 as a point on link number 3, having the instantaneous relative velocity to be 0 with respect to a coincident point at this instant, a coincident point on the link 2. Now if you see a coincident point right now here, I can say this as the joint between link 2 and 3. So this link 2 joint is a coincident point for 2 and 3. So at this instant I can say, very well say, that this joint is the instantaneous center of rotation for both these bodies. So they are the, so that means this instantaneous center is for body 2 as well as body 3. So fine. So the instantaneous center of velocity we can as well express with respect to the fixed link as well. So in a if we see in a mechanism, there are number of rigid bodies interconnected to each other and in plane motion. So all the bodies are moving on the same plane and there is a fixed link frame, right? So out of these n-link mechanism, we get number of relative instantaneous centers, and the relative instantaneous center with respect to fixed link are nothing but the absolute instantaneous centers. So then we can say for an n-link mechanism where we are considering there are n number of links in the mechanism. For n-link mechanism, there are, I can say, NC2 relative instantaneous centers, right? And so we are considering 2 links at a time. So that is why we can say NC2 as the number of instantaneous centers. So we can say, so if we see this, so number of instantaneous centers in an n-link mechanism will come out to be, so if we take this factorial, so I can say it will be n into n minus 1 by 2 will be the number of instantaneous, the relative instantaneous centers for a given mechanism. Now, all these links in a mechanism, they are interconnected to each other. So there is a formation of pairs. So there are various pairs. We have as well gone through the types of pairs. So there are revolute pairs. There are prismatic pairs, right? Then there are higher pairs as well. So higher pairs, in higher pairs we know there are rolling pairs. So if we see for revolute pairs, the instantaneous center will be always the center of rotation of the links. So that means, so if there are these two links and this is forming a revolute pair. So for a revolute pair, the center of rotation for these two links will be this joint. So that means this joint becomes the instantaneous center of rotation. Then for prismatic pair, now for a prismatic pair if we see, so for example say the slider, so the motion is linear. So for this the instantaneous center will lie at infinity, right? Because for this body having linear motion, we can say that the center of rotation for this prismatic pair or this body or this link or the slider, the center of rotation will be at infinity. So the instantaneous center for such bodies will be at infinity. And for higher pairs with kinematic constraint, now when we say kinematic constraint, that means say this is a rolling pair without slip. So there is no slip. So if there is no slip, in that case the point of contact between body 1 and body 2 will be the instantaneous center. And higher pairs with general pairing, if we say a general higher pair, that means maybe slip is allowed. So in that case the instantaneous center will say, for example, if this is one body and this is rotating about or this is rolling on this body, so if it is with no slip, then the point of contact will be the instantaneous center. But if a slip is allowed, then whatever will be the common normal for these two curves, the instantaneous center will lie on the common normal of these two pairing. So that is how, so we can understand, we can determine what is the number of instantaneous center, as well as we can make out where these instantaneous centers are lying. So now we move on to the next part. This is the Ehrenholtz-Kennedy theorem for three instantaneous centers for a given mechanism. Now this theorem is helping us to do the velocity analysis when applied to a mechanism. So it states that, what does the Ehrenholtz-Kennedy theorem states, that if three bodies are in relative motion, then the three instantaneous centers are collinear. So when there are three bodies having relative motion with respect to each other, then if we see the three instantaneous centers of rotation with respect to all these three bodies, it will come out to be collinear. Now they might not be interconnected. That means the body what we are talking about, they might not be interconnected, but there do exist a relative motion between them. Say for example, if we consider say a 4 link mechanism like this, right? So this is link number 1, this is link number 2, this is link number 3, this is link number 4. So what does this statement means is they might not be interconnected in the sense, see these 1, 2 they are interconnected, 2 and 3 they are interconnected, but 3 and 1 they are not. directly interconnected, but definitely for this mechanism 3 is having definitely a relative motion with respect to 1. So here we will try to understand that how this is possible. Now to prove this condition, what we are this, or I can say that this condition is proved by contradiction. That means we will be considering body, we will assume them to be non-linear, and we will show that this is impossible, right? So by contradiction, that means it will be only possible when these three centers they come collinear, then only the motion can exist. So in that case, if the consideration of 3 bodies, that means at least 3 bodies we need to consider. So let us say we consider 3-link say mechanism in this way. So these are the joints. Say this is link number 1, and we assume this link number 1 to be as the frame. This is link number 2, and this is link number 3. So we can say that for 2 and 3, so this is I23. For this 1 and 2, this can be I12, and for 1 and 3, this will be I13. So if we consider this here in this case, so body, now if we say that, say this is turning, say the body 2 or link 2 is rotating in this fashion. If it is so, it will try to take this joint, right? So with it, so I can say that the instantaneous velocity, whatever may be the situation, if it is rotating, so instantaneous velocity of I23 will be perpendicular to I21, I23 line, right? So it will be perpendicular to, so this will be the instantaneous velocity, or for that matter if I say, so this will be the instantaneous velocity for the link 2 when I consider this to be on link number 2, and the instantaneous velocity of the point I23 with respect, when I am considering, because this is a coincident point, so if this with respect to this line, then the velocity vector for this will be in this direction, right? So now if you see, if we see this condition, now if this is a coincident point and this body has to move, it is the same point, then in that case, if this is say I12 and this is say I13 relative to 13, if I say, so in that case I must say that this velocity must be equal to this velocity, but these two velocities are at 2 different directions. That means their motions are in 2 different, so that means this velocity vectors, they are moving away. So it is understood that in this case, then that means this cannot exist, this situation cannot exist. Now for if we improvise this configuration, say this is link number 1 or this is link number 1, this is link number 2, and let us say this is link number 3. So this is joint, right? So try to understand this. So this is link number 1, this is link number 2, and this one is link number 3. Now if you see this joint, now if this link number 3 is turning in this direction, the velocity vector of this joint with respect to the link number 2 will be this, if it is moving in this direction, and this joint with respect to 3 will also have the same direction. So both these velocities will have the same direction. So that means we can say here, until and unless these 3 instantaneous centers they come along a line, or until and unless they are collinear, this cannot exist. So thus we have proved the statement for Ehrenholtz-Kennedy theorem, where it is stating that if 3 bodies are in relative motion, then the 3 eye centers, they will be always collinear. And this particular theorem is then helping us to determine the velocities of various joints and do the velocity analysis. So we can then find out the unknown velocity conditions. So that's all for this session. So then we can apply this Ehrenholtz-Kennedy theorem for various mechanisms to determine their velocities.